Okay, so today I'm going to talk to you about things that have been extracted from 3 different papers with my collaborator Nathalie Ayi, and it's about interacting particle system on both deterministic and random graphs. Okay, so let me start by giving you the context. The one is we will be interested in is the one of social dynamics models. So basically, you have an agent, or we'll see sometimes particles, and so agent I, xi is the opinion of agent I in most of the examples that I will give you. And what is the system, what describes the system is the fact that so agent I will interact, discuss with agent J, and depending on the strength of their relation, which is modeled by Aij, which is the interaction coefficient, it will impact the way his opinion will change. Okay, so a typical example is the one of the Excelman-Krauss dynamics, where Aij has the following form. You take A, which is an influence, sorry. Okay, I spoiled a little bit, sorry. So A, which is an influence function, and so Aij will actually depend on how close or how far your opinion are. So basically, it looks a bit like in life. You maybe have observed that when you discuss with someone, if your opinion are very too different, if you're at different spectrum of the political opinions, there is few chances that when you will exchange, you will manage to make you change your mind. So this is the idea behind this model. Okay, so when you're interested into this kind of model, there are plenty of questions that you can ask yourselves. I've listed 2 big classes of questions. The first one is the large time behavior. So what are the patterns which appears when you're dealing with this model in the long terms? So for this type of model, the Excelman-Krauss dynamics, which is also called consensus model, well, you can observe that most of the time, so here is the time, okay, and here is the different opinions. So you can say that naturally a lot of models go to consensus, so the population tends to align its opinion and have a unique opinion at the end. Or another fact which happens sometimes, it's the clustering. So at the end you have a finite number of opinions. This is something that, for instance, you can observe on social media when you can see that you have different polarized groups with very different opinions, but which are shared among their groups. Okay, so you can ask yourself those type of questions, but this is not the one I'm going to discuss today. I would be interested into the second big class, which is the large population limit. So n is my number of agents. What happens when n goes to infinity? So there are different approaches when you are interested into the large population limit. The first one that I'm going to mention, which is the classical one, the oldest one, the one you're, I think, all familiar with here, this is the mean field limit. So in the mean field limit, you have a change of perspective that you're no longer interested into the trajectory of each particles, but you're interested into the density of particles, probability density. So you would describe the behavior through the probability density, and so it is known. So now I would say, quantity of interest is a measure which will represent, so mu Tx will represent the density of agent with opinion x at time t. And for instance, in the case of the Excelman-Krauss dynamics, it has been rigorously studied and established that when you pass to the limit, you obtain non-local transport equation, which looks like that, where you can identify here, A, the function who were there to describe the type of interaction that you can get. So of course, the problem with this approach, the classical mean field approach, is that you need some property for your particle system, one which is called indistinguishability. Mainly, if you play and change the name of your different agent, the dynamics will not change. Okay, it does not change. Somehow, it does not change it does not see the identity of the different particles. So of course, once you've said that, well, it reduces the span of the model that you are able to study through this approach. Hence, the second one that I'm going to discuss today, which is based on some result from the graph theory. So the best, I think, is to explain it with an example, which is the L nearest neighbor, which is a typical model where this approach is interesting. So the L nearest neighbor, imagine all of us in this room. I put all of you on only one line, and I'm telling you, so from now, you can only interact with the two people to your left and the two people to your right. Okay, remind those people, and then you can go wherever you want, but you only have the right to discuss and to make your opinion change with those people. Okay, so this is significantly different from what I've been describing with the Excel-Krauss approach. Because in the Excel-Krauss approach, the only thing that mattered was how far your opinions were, okay? If they were sufficiently close, you were able to interact. If they were too far away, you wouldn't. Here, you could have the same opinion. If you were not seated 2 seats beside this person, you couldn't interact. So basically, what we're saying is that there is a graph associated to your particle system. So in that case, this is the graph which is described here, where the vertices are the different agents, and the edges here are the ones which are, in terms of identity, not too far away from you. So this is one way of representing it, but I'll let you look one side while I'm drinking. Okay, so this is one way of representing it. Another one is the following. So you will introduce this function, which is right here. So how do you build it? So you take your interval 0, 1, you divide it into n sub-intervals, and you do the following things. So let's call this one I subscript I and I subscript j. And you say, if psi zeta belongs to I times ij, where ij is one of the edge of the graph, an active one, then you put a 1. And if not, you put a 0. So for those who are familiar with some notion of graph theory, actually when you do that, you are just drawing a pixel version of what is called the adjacency matrix, the one who tells you with who you have the right to interact. And so the advantage of this representation, which is right here, is that now, if I'm telling you that, okay, I want to put n to infinity, for instance, in that example, you will guess what will be the limit, okay? You will guess what the limit object is, and this is this limit object, which will be very important in the equation that we are trying to reach. And so typically here, what you will guess is that you will obtain an indicator function that you can see here. And this object here is a graphon. And this is the one that will appear in our equation when we will pass to the limit. And so typically, so when you do large population limit for non-exchangeable particle system, there are 2 different approaches. You can reach what is called the continuum limit, and you can reach what I call the non-exchangeable mean field limit. Today I'm going to focus on the continuum limit. So in that case, this is reaching this equation, which is right here, and I will tell you the exact result, how you pass from your particle system to those type of equation, where you can observe that in that example, the graphon is here, okay? There is actually a second approach that I will briefly mention today, which is, okay, so I will say it after. Let me be first precise with the result, and then I will discuss the other approach. So if I want to state a little more precisely the results, okay, I have my interval high, I divide it into n sub-interval as I told you. And so far what I discussed was what is called simple graph. So your edge is active or not. But you can also be interested into weighted graph. So here, this is to follow the idea that I was discussing in the introduction, that not all of your interaction in real life matters all the same, okay? And so here you take a graphon, W, and so the graph of your system of particles will be built by averaging your graphon on subintervals. A graphon is the function W from I squared to R. This is all you need to know. Okay? Okay. Sometimes they add a symmetric property, etc., etc. Here, you just need that. Okay, so far. Okay? So this is what will play the role of your weights. And so you build your weights of your particle system with the graphon by averaging it, and you're interested into the following particle systems where, so now your particle interacts with a certain way, so you can represent it this way. So here, for instance, it's a symmetric graph, meaning that the weight of 1 on 2 is the same as the weight of 2 on 1, okay? And so the precise result is the following. So this is a result which is due to Medvedev, which is if your graphon is bounded, then you can have the convergence of this quantity that I will not precise yet. I will do it after, but so far you need to know that this is associated to your particle system. It will converge to X, which is a solution to this integral differential equation that I will call continuum limit equation of our graph limit equation. Okay, so this is the convergence result that we call the graph limit. And so as I was mentioning, this is one approach, the continuum limit, but you also have the second one, which is the non-exchangeable mean field limit. So if I go back a few seconds to the exchangeable particle system, the one where when you change the identity of the particles, the dynamics does not change, I've shown you that you can obtain a non-local transport equation. Actually, you can also do this kind of result for now non-exchangeable particle system with some weights here. And it has been done a lot, but a lot of different people that I've put a few of the paper which appear. So you see now that actually you obtain at the limit of measure, but which also depend on psi. Psi, which play the role of the identity of the particles living in 0, 1. And so here you see the graphon will appear here. And so this is what we call the non-exchangeable mean field limit. A lot of people work on that in different framework, from dense graph, sparse graph, for regular graphon, non-regular graphon, etc., etc. A lot of literature. So if you're interested into this approach, I invite you to read a review paper that we released just last week with Nastasia, which explain a bit those two approaches. And I would say more interestingly, which explain also the link between the two approaches, because that was not so clear at the beginning when we started working on that. Okay, so the model that I'm going to be interested today, the first one, is a kind of a variant of the Excelman-Krauss approach. So meaning that we still are interested into xi, the opinion of agent I, but now we are also interested into mi. And what is mi? It would be, let's say, the charisma, the popularity of the agent. And so what does the model describe? It describes the fact that when you interact with someone, the more charismatic, the more popular this person is, the more it makes you change your opinion. And the model also describes the fact that popularity is not always the same. I mean, you can be popular one day and then lose popularity, etc., etc. And the way that your popularity move depends on M, which is the charisma of all the agents, and X, which is the opinion of all the agents. Okay? So now we add a new parameter. And so the question is, for this model, which is a little bit more complex, can we still obtain the continuum limit? And so the answer is yes. This is what I'm going to explain. And then in the second part, I will do some links with the classical mean field limit and a word about the non-exchangeable mean field limit. And on the time that I would have left, I will explain you what we can do when now we're interested no more in deterministic graph, but in weighted random graph. So the model that I'm describing can be represented on a graph, which looks like that. So several differences with the one I have been showing you before. The first one is that it's no longer symmetric. You see that the weight of 1 on 2, it's M1. For this edge, this is not the same that the weight of 2 on 1. So this is a directed graph, okay? And the most important thing, this is the weight depends on time, and the weight the evolution is coupled with the evolution of the nose. So in the literature, what you can find, the term that you can find for this type of graph is that they are adaptive dynamical networks or co-evolutionary. Okay, both terms are, can be fine, and this just explains you that the structure that describes the interaction between the agents can itself evolve, okay, which kind of look like life too. You can decide to not discuss anymore with people that you do not agree at all anymore and do not share values anymore. Okay, so can we do the graph limit for this model? Okay, so now I'm going to precise a little bit something that I've been quick before. The thing is, we are trying to compare things which does not exactly live in the same world. We're interested into the discrete particle system, where we are interested into vector from RDN, Rn for the opinion and the weights. And we are trying to compare that with my solution of my integral differential equation, which is the function x of xi, okay, so which will live in a certain space, LP space. So we have to find a way to make those two things speak. And so how will you do that? Well, just by nothing more complicated that this picture show you. You build what is called x subscript n and up subscript n by transforming it into a step function. Okay, you add this dependence on xi this way. Okay, but actually you also have to do it in the other way. Now you know how to go from discrete to continuous, but you also will need to go from continuous to discrete. And this you can imagine. You just, for instance, for your initial data. When we will start with those will be the initial data associated to the graph limit equation, and we will build the initial data for our particle system with this function, and we do it this way. So we divide it to n sub-intervals, we average on each sub-intervals, and this is where we will make our particle system start. So we have to do it for the initial data, but we also have to do it for the weight dynamics. So remember, so when we were in the Medvedev results, what it was doing is that actually W, which will be the graphon appearing in the limit equation, this is what it was using to build the weights for his microscopic dynamics. Well, we will do something which is quite similar, because here, psi, which will be the function at the limit which describes you the weight dynamic. This is the one we use to build the weight dynamics for the microscopic system. Okay, so this is the same process for Medvedev, just adapted to the co-evolutionary framework. And so now we're happy because, okay, we try to compare two different objects, but we find a way from them to communicate even if they do not live in the same world. And actually, once we've done that, we've done a huge part of the work. Why? Well, because of that result, which is here. Because actually, we can prove that being a solution to the particle system, this is perfectly equivalent to x subscript n and m subscript n to be a solution of that system of integral differential equation, which is right here. And once we have written it this way, well, it's really not that far away from the equation that we're trying to reach. And so we did a good part of the job. So those two things are perfectly equivalent. And this is the form that we will use to try to reach the continuum limit. So I did not show you the continuum limit yet, so let me show it to you. So this is the equation which is here. And so if I'm interested, if I forget for just a few minutes the graph limit question, and I'm just looking at this equation, well, it is well posed. So here you just need some regularity assumption. Okay, here we suppose phi of 0 equals 0. It is not necessary, just simplify the computation. But what we really use is the regularity. So we need Lipschitz continuity on phi. And we also need for weight dynamics that it's uniformly Lipschitz with respect to x and m. And a very important point, we need this sublinear growth bound because it will prevent the weight to explode, and actually it will put it in a framework where the weights will be bounded, and this is consistent with the Medvedev approach because Wij, you can obtain graph limit result for bounded graphon. Okay, so to be able to do the same approach, the same proof, adopt the same proof, we need this bound. And so, okay, under those assumptions, this equation that we try to reach is well posed. And then the result who tells you that you reach it is the following. So under those assumptions, being a solution to that I recall is perfectly equivalent to having a solution to my particle systems. Well, we can prove that this x subscript n and m subscript n converges into those space of function to x and m solution of this equation. So basically, we're saying that even for this co-evolutionary graph particle system, we can do the graph limit. Yeah, this is just the operator that transforms a continuous function into a discrete one and a discrete one into a continuous function.
So then you transform your initial data in a discrete?
Yeah. Well, because actually we initiate the position of our particle system with respect to the initial data of the continuous one, okay? Because at some time we will use stability estimates. But to reformulate our problem, we need to transform our particle system into a function which lives in the good space. So,
when n goes to infinity, it's identity, right?
yeah. So, okay, so this is the graph limit result, and just to give you a sketch of the proof, well, this is mainly stability estimates. So how do you do that? So you're interested into the difference between those two different functions. And so, well, you sum your equation and you integrate. And when you do that, then you will obtain those inequality by using your regularity assumptions. So basically here, this is at some point you will use your Lipschitz continuity of phi. The m bar that you see here is at some point you will use the fact that the weight that you have built are bounded. Here at some point you will use your the Lipschitz continuity of psi, etc., etc. You really obtain those inequality through the regularity assumption on your different functions. And then once you have done that, well, it is done. You obtain that, you do Grunwald lemmas, and then you build your initial data for that to converge. So this will go to 0. And here I will not go into detail, but this is a term that you can easily show that converges to 0 too. So basically, so this is the same approach that Medvedev did. We just add additional term and more computation, and so we have to be a little more careful. But we were quite surprised to see that, well, it works quite well. Okay, so let me illustrate this with a few examples. So, okay, so this is toy models. I do not pretend that they are very sophisticated, but they allow to see different things. So, for instance, let's suppose that you have a population that you divide into K groups. And so in each group, you say that you have two types of person. You have leaders and followers. Imagine you are in X, the former Twitter, for instance. You have leaders, you have followers, okay? And so we say that the weight dynamics, how does it make your system change? We say that when you are a leader, your weight increases proportionally to your own weight and to the total weight of the followers of your group. And when you are a follower, your weight decreases proportionally to your own weight and to the total weight of the leaders of your group, okay? And so when we do some simulation, what do we observe here? So let's say that we have only one group of 20 agents with 10% of leaders, so 2 leaders. Here is the time. Here is the different position. Here is the different weights. We can, you can observe first that at the end, the weight of the population is divided into the 2 leaders. And something that is interesting is that, okay, in that case you reach consensus, and the consensus it is at a position which is not so far away from the initial position of the leader of the group, meaning that the population tried to align his opinion with the leader of his group. Okay, and so how do we illustrate the graph limit? Okay, so let me explain you those 6 pictures. So how do you have to read it? Here, it's my interval I, where my variable psi lives in the x-axis. In the y-axis here will be my opinion. Here would be my weights. In black, this is my solution to the graph limit. In red, this is my step function that I build from my particle system. So x subscript n here and f subscript n here. So first, you can see our result of graph limit because those two curves behave the same, okay? And you can also observe, this is a different way of seeing the consensus. We are not yet at the consensus, but if you reach the real consensus, this will be completely flat. And you can observe too, what I was saying, that at the end, the weight is split only between the leaders of the group. Here, the 10% of the population, okay? So this behave like the dynamic I showed you, and more importantly, you can observe the graph limit result that I was claiming that we obtained. And a second example, which is interesting, is the following. So now let's say that you have 2 different groups, and so 1 leader in each group. So what you observe here is that you have a leader who takes a lot of the weight much more quickly and much more than the other one. Why does it happen? Well, if you look at here, okay, so it's not t equals 0, but it's not so far away, so it did not change that much. You can see that here, the total weight of this group is much bigger than the total weight of this one. And so we are just saying that's something that is, maybe not so moral, but it's better to be popular among popular people than being popular among people who are not so popular. Because you can observe that, okay, not only this is the one who takes most of the weight, but also at the end, the consensus is reached at a position which is much closer from the one from the leader among the popular people than the leader among people not so popular. Okay, and we're gonna also observe the graph limit results.
Do you have any conservation of mass for the weights?
Yeah,
Yes.
Absolutely. I didn't say it, but sum of our I of psi I equal 0. Yeah, definitely.
You cannot create popularity from nothing.
No, that's right. That's right. Yeah, and we kind of needed the conservation. Okay. Okay, so yeah, let's go back a few minutes for to the mean field limit, and I will try to make you understand the link between the different approaches, because I think this is very interesting, because actually you have one way to go from one to another. So if I go back a few minutes to the classical Excelman-Krauss model, so you're all familiar here that the path to obtain the mean field limit can be through the empirical measure, which is the quantity which is right here. And so the main observation is that this empirical measure is itself already a solution of this non-local transport equation, and then you prove stability estimates and you have your results. Okay, continuity with respect to the initial data, and you have your results. So now let's go back to our case. In our paper at that time, we decided to look at a slightly different empirical measure where, because the variable m, the weights, play a special role, we decided to look at this special form, okay? So we were interested into the total weight associated to an opinion. Okay, and so the first thing that you observe is that, okay, this is a slightly different invariant measure, but like the first one, it does not see if you change the identity of the particles, it will not see it. But now there is a new thing which is invariant too, because of this new form. This is what I call the grouping of the agent. So meaning that, okay, if I have different agent at the same position, what I'm interested is the total weight at that position, okay? And I don't care how it is split between the different agents. So this is what I call the grouping of the agents. So if I show you a precise example, I have those two systems of particles here, who are, so y and x and y, which are exactly at the same position. And so if I have two particles at the same position, here, for instance, my blue particle has a weight 0.5, my red one 1.5, so I have the weight 2 at that position. And here I have the weight, my blue particle at the weight 0.75, the red 1.25, I also have the weight 2. So those two systems you see are different, but they will have the same empirical measure. My empirical measure will not be able to see the difference between those two systems. And so the thing is, I told you that the mean field limit is completely linked to the empirical measure. So the systems that you are able to study for this approach must respect the property of this empirical measure, okay? And so basically this makes sense only for a system which preserve this indistinguishability in the sense that I just described. So what do I call preserve indistinguishability? It's to say that if I start from a system which is the following, so which will mainly correspond to the image I just showed you. So you have two different systems, x and y. Okay, if you look at one system where there is only one particle at one point, there is also one at the other system, so they have the same weight. But if you look at a system where for one system you have several particles at one point, well, you will have several at the other one too, and even if it's split differently, the total weight is the same, okay? This is what is written here. Well, it has to stay true for all time, okay? So this is what we call preserve indistinguishability. And so for those systems, those are the ones for which it will make sense to look at the classical mean field limit. And what is the equation that we are going to be able to reach? Well, let's do the computation, the classical computation on the empirical measure, which makes appear the equation. So how do you do that? So, well, you are interested into this quantity. So you write what is your empirical measure. You make appear your derivative of mi xi. You replace your different expression, and then you rewrite, you make appear again the empirical measure, and once you've done that, you obtain this equation. So this is interesting to see that with this approach, now you have a non-local transport equation with a source term, and this is the source term which makes appear the weight dynamics. So this is how the fact that now you have weights that can evolve appears in your equation with this particular form of empirical measure that we have chosen. And so for this, okay, so as I was saying, since you want you can only do that for systems which preserves indistinguishability. Again, we are back at the beginning where we reduce the span of the model that we are able to study with the classical approach. And so for those special class of weight dynamics that I will not write here, but maybe after, for which you can prove that you preserve indistinguishability, you have two approaches, actually. You have the classical one that I just recall in the classical case, meaning that, so this was done by Anastasia in a paper where she did the classical approach. So she did the previous computation, observed that his empirical measure is already a solution to this non-local transport equation with source. And then she proved continuity with respect to initial data. Well, okay, so stability estimates as usual. You can do that, but what I'm more interested today is to show you that you can actually reach this equation passing through the graph limit. And why is that true? Well, because of some computation that I just did, and I will remind you. So first, let me write here the class, the general form of the special class of weight dynamic for which you can do that. So mainly the most important point, a class of dynamics which preserves indistinguishability. And for those weight class, so first I have to say that, okay, you have to redo the proof for the graph limit, because unfortunately the one who preserves indistinguishability does not fit all the assumption that we use to prove the graph limit. So you have to work a little bit, but that's okay, it works too. And so now that we have the graph limit for those special class of weight dynamics, we built here this measure, mu tilde, this way. So maybe you can sense it. It's kind of a continuous empirical measure, right? And so, well, you can do very, very similar computation to what I just showed you for the particle system. For here, this probability measure. And you will obtain this non-local, this transport equation with a source. Okay, so this is very the same computation that I did before, but in the continuous case. And so what are we saying? We are saying that, okay, so now if I have a solution to the graph limit, I actually can reach this non-local transport equation. So it gives you a new path. And so if I put it all together, what I'm saying is that if I'm starting from my particle system and I'm building this empirical measure here, well, I can prove that it will converge to this measure mu tilde built through the graph limits, and so you will reach the mean field limit this way. Okay? And so how do you do that? I can give you the idea of the proof in 2 lines. It works why? Well, because your empirical measure, you can rewrite it as a continuous empirical measure where m and x from the mu tilde have been replaced by m subscript n and x subscript n. This is the same thing. And so once you have written it this way, you see that you will basically use the convergence of mn to m and xn to x to prove your results. So once you have done, actually, you already done all the work when you have proven the graph limit result. Okay, so let me show you an example before finishing to show all the link between the different approaches. So we call this one the least influence, gain influence. So this is the following. So let's call Eg to I the influence of J on I. Okay, so this is the influence that arrive on I. So we can compute the total influence on I by summing over J all the influence. And so we can do that for all the agents, and so we can have access to the weighted average of the total group in the population. And so what our dynamics does is the following. If the total weight on I is lower than the average on the population, so meaning if you are less influenced than the average, let's say if you are more difficult to convince, if you are more reluctant to conspiracy theory, etc., it makes you gain popularity, okay? And on the contrary, if your the influence on you is bigger than the average, so if you're someone very easy to convince, it makes you lose popularity, okay? So this is what the model described. And so we did a few simulations. So here we take the Excelman-Krauss model, where we did a variant of that. And we take the case with the influence function with compact support, okay? And so basically, we could see at the beginning which were the agent, which were the least influence. It was this one and this one, because they only have people on their left, and here he only have people on his on their right, and here on his left. Okay, so those are the 2 persons who are the least influenced, and you can observe, which is consistent with the model, that these are the 2 for which at the beginning the weight increases because they are the least influenced. And then you can observe that the red one, at some point, he joins the group. And so he becomes more and more influenced. And this is why his weight is decreasing here. Okay? And so about first the graph limit and then the link with the mean field limit. So here is my interval I with my parameter xi. So here is the opinion, here is the weight. And so similarly to what I've been showing you before, you have the graph limit, but now for those special class of weight dynamics, it still works. So you can observe that you have the convergence, this time not to consensus, but to cluster. It will be at the end a real three-step function. And so what is very interesting, I think, is the following, is that now, okay, we have the graph limit, which still works, but we also have the right in that case to do the classical mean field limit. And so we can compare the three things. So here, beware, here it really will be the opinion. Here it will be my different measure. So the red one will be my empirical measure. The black one will be what I call mu tilde, which is the measure which is built through the graph limit. And the blue one will be my solution to my non-local transport equation. Okay? And so with my results, it should all behave the same way. And okay, this is what we observe. So you see, which is consistent with our theorem that, okay, the empirical measure is well approximated by mu tilde and by solution of the non-local transport equation. And this is a new, a third way of seeing the long time behavior at the end. Here, with the cluster, we should have three different directs. And to finish, to give you the picture, so here is a picture that we took from the review paper that I was mentioning. So let me explain you what we did. Okay, so it was not so clear at the time we write this first paper, but now we see more clearly all the links between the different approaches. So what I've been explaining you in details here is this hour which is right here. This is the graph limit. So you start from your particle system, you obtain this integral differential equation limit here. Okay? What I just explained you is how from the graph limit you obtain what I call exchangeable mean field limit. I just show you, and I mentioned you that actually you can also do directly this arrow here. That was the paper of Nastasia through the classical approach. So you can do it directly through stability estimate, but you can also do it like I did by doing first the graph limit and then doing the computation, which links the mu tilde defined with the solution of this equation with the solution to this non-local transport equation with source. But actually, you can also reach the one that I mentioned before, which are the non-exchangeable mean field limit, where now you also have the xi parameter, which still keep tracks of the identity of the particles. And so how do you do that? Well, you will just define slightly different continuous empirical measure. And for those different empirical measure, you will do the equivalent of the computation that I show you, and you will obtain those different equations. So you can reach, okay, so this gives you the full picture. I think that it's really interesting to see how everything is related. But basically, you have a different level of description, exchangeable, non-exchangeable, probability on X and M or just on X. And you can link all of them together. Okay. So in the time that I have left, I would like to say a few words about random graph. So far what I've been discussing is only on deterministic graph. Now we'll be interested into random graph. What is a random graph? It's a graph which is generated by a random process. So basically, well, the typical example is the Erdős-Rényi graph. So how do you build it? You consider an edge, you take a coin, you toss a coin, and let's say if you have head, you draw your edge. If you have tail, you do not draw it. Okay? So this is how you build it. So here's an example of some simulation, some realization for N40 and 60 in the case of a balanced coin. So, well, this is a perfect example of a random graph. Another one is the small word graph. How do you build the small word graph? You start from the graph that I've been showing you before, the L nearest neighbor. Okay? In that graph, you consider an edge which exists, and then you toss a coin. And with a certain probability, you destroy this edge and you build a new one randomly, and with another probability, you keep it. And so here you can see that the probability to destroy the edge starts at 0 and increases from left to right in that example. So you can see that as kind of an interpolation graph between a deterministic one and a completely random one. Okay? Another example that I will be extending on is what is called W random graph. So this will be random graphs which are built through graphon. So how do you build a W random graph? So you take random variables, xi, no xi, so beware now xi are random variables, which still lives in 0, 1, but they are taken uniformly with a uniform law. And so how do you build your graph? You do the following. So you're interested into the edge ij, and you toss a coin, and with probability w of xi xij, you have a head, you draw your edge. With probability y minus w xi xij, you do not draw it. So this is how you build a W random graph, so a graph built with a graphon, a random graph built with a graphon. And so, of course, so now that we have those new type of graph, which are random, the question is still the same. So if we are interested into dynamical systems on those graphs, well, if we write them, this is nothing else than saying, in that case, that here, the weight which is here, it just follows a Bernoulli of parameter w xi xij. Okay? And so the natural question is, okay, despite this new randomness, can we still, so I just rewrite the systems here, can we still do the graph limit? And so that was answered by Medvedev, which obtained the convergence to this equation, which is right here. So first thing that I would like to say is that you start with a system of particles which is random, because built on a random graph, and at the end you obtain an equation which is purely deterministic. So in some sense, well, you are doing kind of a law of large number, okay? So first thing, and so let me show you more precisely the statement of this result. This way I could explain you how our result is slightly different. So what does he do? So he takes a graphon, and the main restriction I would say is that his graphon and his dynamical system must satisfy this inequality, which is this bound, which is right here, and which is purely technical. Okay, there is no modeling assumption to justify it. It's just purely technical. And so it makes it kind of a Heath theorem, because a priori there is no guarantee that your dynamical system will satisfy that for all t. Okay, and so under this assumption, the type of result that is obtained is that he obtained a convergence in probability of the solution to his particle system to the projection of the solution to the integral differential equation on the xi1, xi2, xn. So this is in the context of random graph. What is the graph limit? This is the type of convergence that is rich. Okay? And so when we found this paper with Nastasia, we already have done the first one that I showed you, and so we were very interested into weights. And so we were saying, okay, so this is interesting, is doing that for simple graph, because its edge are Bernoulli, so it's 1 or 0. So we were wondering, okay, would it still be possible to do it for weighted graph? Weighted random graph. So first we did a bit of bibliography to see what type of weighted random graph already exists in the literature, because we were not so familiar with that. We find a few, like for instance the Garlaskelli model, which is the following. So again, you take a coin, you toss a coin, and this time you toss a coin and you keep tossing it until you keep having head. And you stop at your first tail. And you count how head you have. And this gives you the weight for your edge. Okay? So that was first. So this is what describes this particular weighted random graph. We found a few others, but what was striking is that, okay, there are a few, and it was always very specific case, and they were looking at very specific question and no question of type large population limits. So the first thing that's kind of interesting, I think, in our paper is that we provide a general framework which contains all the approaches. Okay? And how do we do that? We just introduce a new notion that we call a Q-weighted random graph. What is a Q-weighted random graph? Well, you have here a function which at Q psi zeta associate a probability. And so we're just saying that how do you build a Q-weighted random graph? Well, it's a graph from which the weight that you attribute on the pair ij, it is done through the probability Q of psi j. Okay? And so once you have written it this way, well, actually you can fit all the existing model in that framework. You just have to specify the form of the low Q. And so, for instance, in the Medvedev case, you just have to rewrite that your weight is random, is a Bernoulli of parameter W psi zeta. For the Garlaskelli model, you specify the process that I described you, that you just toss your coin until you have a different issue, etc., etc. All of them can be described in this framework. And so the question, the natural question is that, okay, now if we are looking at a system of particles on those Q-weighted random graph, can we do the graph limit, and what do we obtain? And so, yes, we can do it. And what is very interesting is that what do we obtain? What plays the role of the graph on? Well, it's actually the moment of order 1 of our law. And so here you see appearing the moment of order 1. And so first thing is that our good news, our result contains the result of Medvedev, because you can directly see here that if, for instance, it is Bernoulli of parameter W psi zeta, you find the Medvedev result that I've shown you before. Okay. But actually, it does not only contain Medvedev result, but it improved its result, because we actually need less assumption, and more specifically, we do not have this if condition because we do not prove it the same way it did. We did a different proof. And so what is our framework? So we still need some regularity, but what we work a bit hard for is that so Medvedev, it's simple graph, so his edge is 1 or 0. But what he crucially used in his proof is the fact that his edges are bounded. And we wanted to have the possibility to work with non-bounded weights. And so we managed to have only assumption on the first 4 moments of the law. And under this assumption, we are able to obtain the following results. We have a quantitative convergence of the system to the solution to the particle system to the system of the integral differential equation projected on the xi1 side. So again, as I was saying, that so we managed to prove this continuum limit for weighted random graph, so a class slightly a class more general than the one for which it was we were able to do that, and under less restrictive assumption. And so if I want to finish with some illustration, for instance, let's go back to the Garlaskelly model. Okay, so in that case, I already wrote the law. So now we have to compute what plays the role of the graphon, that I recall is the first moment of my law Q psi zeta. So here it's a case where it does not depend on psi zeta, it's constant. And so I know that my function at the end will be this equation where I replace my first moment by p over 1 minus p. And so if I want to show you the picture of the matrices, the pixel matrices, so we put n bigger and bigger, and so we generate them, okay? And so we compare it with the graphon at the end, which is constant in that case. And so you can see that when you will put n bigger and bigger, you will have this phenomenon of visual harmonization, and you will tend visually to this constant graphon, which is here, okay? And the convergence result is the following. You can prove that, well, when n goes to infinity, those things goes to 0, okay? And I will finish with another one that, okay? And let me finish with the weighted small world network. So what does it describe? So it's a weighted version of the small world network that I explained you. So now the only difference is that when you decide to destroy an edge, you randomly create a new one to which you randomly attribute a new weight, okay? So this is just what I just told you in one sentence, which is written here. And so when you compute the first moment associated, this time it's kind of more interesting because it depends on psi and zeta. And so the picture is more nice, I would say. And so you can compare, if you do some simulation, some realization of your pixel random matrices, you can compare it with the graphon, which I recall again is the first moment. Okay, so you see, you visually see the convergence, and I did not put it, but you can also plot the convergence result, the graph limit convergence result. And I will just finishing by mentioning that, okay, what I describe you is what is called random case, in which the xi, xij are random. There is also a version where the xi, xij are deterministic and live in sub-intervals. And then the randomness comes from the fact that you build your edge with probability W of xi, xij, but xi, xij are deterministic. In that case, we can do an alternative proof. And there are also another part where we're interested into blinking systems. It means that at a regular interval of time, our graph is regenerated. And the interval of time is epsilon, and so we are interested into what happened with this interval of time goes to 0, and how this limit is compared with the limit n goes to infinity. And I think I will stop here. Thank you for your attention.
So thank you, Nathalie, for your very interesting talk. Are there questions? Yeah, I need to go to.
Questions? Do the large N and large T limits commute? Like, can you deduce like long-term?
Large T time?
Yeah.
We really never do large T.
No, but do they commute with the large N and large T, or does your limits in large N depend on T?
Yeah, definitely.
Okay.
We use the fact that it's on finite interval time.
Okay.
And we will not know so far how to do that without that.
Is there hope that the macroscopic equations can give you insight into the long-term behavior of the finite particle system?
Maybe. So far we do not manage to do that better.
So in this, when you're modeling opinions, like the X, the opinion is something that you can observe. That at least in social media, people express their opinion, and so you observe it. You can know the graph, but you don't know the weight. You don't know the influence, and typically that would be a quantity of interest. And so, those large population models, do they give a starting point to do like inverse problem where you see the X and you want to find the M? Would it be easier with this kind of?
That's a very good question. I can say I'm very not an expert of inverse problems, so I don't know. But you can imagine that yes, this is the type of equation that you obtain at the limit that should be observed to have information on that. But how you do that?
So maybe one quick question, or are there any? So if not, let's thanks Nathalie again.